Hello everyone, welcome back to Kepler. Today we'll be discussing the problems for the Codeforces contest round 1078. This was held yesterday and it had quite a few interesting problems, so we'll be discussing the solutions for some of them. So for the first problem, it is lawnmower. So it is given that basically we have just a minute. Yeah, so you have a fence consisting of n boards, so like this, and you have a lawnmower, right? And the lawnmower can pass through the fence if we remove a W consecutive boards from this, right? So I have to find out the maximum number of boards we can remove so that the lawnmower cannot pass. So basically, you have to find the maximum number of boards we can remove such that we not end up with a hole of size W or larger. For example, here you have 9 different boards and you removed 6 boards like this. So in this way, we only end up with holes of size 1 or 2, and the lawnmower we had here was only size 3, so it cannot pass through any of these holes, 4 holes we have. To find out how many maximum boards we can move from this fence such that we not end up with a hole of size W or larger, right? uh, so this is a pretty straightforward problem. So if you notice first, uh, suppose we had a suppose a W was equal to 3, let's say, and we had a fence of exactly size 3, like 3 boards, right? So in this case, we could have what done is we could have just removed that first 2 boards and left the last board out. So this way, I hold the size 2, and our answer is 2. If we had, say, 6 boards, 2, 3, 4, 5, 6. I think it's an extra. Yeah, if you had 6 boards, we have basically two groups of size 3, right? So we'll do the same thing but repeat it for each group. So for the first group, remove the first 2 and keep the last one here. Then keep the first 2 and the last one here. And this ensures the correctness of our solution because each of our holes will be of size only W minus 1. So lawnmowers cannot pass through this hole. Also, if we have any extra fences at the end, say we have 2 extra fences at the end like this, we can move these as well. So our solution is to group every W boards together, remove the first W boards, first W minus 1 boards from this group, and leave the last board fixed so that we interpret hold the W size W minus 1, and if there are any boards remaining at the end, in case the number of boards is not divisible by W, we remove those as well. So our answer is if we have n boards, right, our answer is n by W, just the number of number of groupings of size W we have, and from each group we remove W minus 1 boards plus whatever remainder we might have remaining at the end, right? So this is the answer for the first question. Now for the second question. So in this question is given that we have in different banks and each bank has some amount of money in it, Specifically, the bank has AI amount of money, and you have to basically transfer all the money into a single bank account. And all interbank transfers are arranged the same way. Basically, we can transfer X rubles, X currency from the source bank, and transfer Y currency to the destination bank. So essentially, we lose X minus Y amount in the process, right? So we have to find out the maximum amount of money we can end up with at a single bank after all the transfers. So for example, suppose if we take a simple example, let's say this one 10987, right? So for 10987, we first transfer all the money. Okay, let's first show it here. So for 10987, and I know one thing, I think it was x equal to 5 and y equal to 4, right? Yeah. So one thing you can do is first transfer whatever money I have in 10, like the first position, to the second bank. So first I deduct 5 and add 4 here, so 13, 8, 7, right? Then let's say I do this again. So let's move to here. So 0, 17, 8, 7. Then do the for the third bank to second bank. So 0 should be 21. It should be 3, 7. Finally, fourth bank to second bank. So this becomes 0, 25, 3, and then this should be 2. Right. And now if you look, our condition was that you have to transfer at least at least exactly 5 currency from in a one transaction. So since these 3 remaining banks, like these 3 banks, have less than 5 in their balance, we cannot perform any more transactions. So final maximum amount raised is 25. Now, firstly, one first claim is we will always transfer. If suppose we want to make the balance at the wide bank maximum, right? So AY wide bank maximum, right? So we will always, our best solution is also transfer all the currency from XZ bank to YZ bank, given X not equal to Y. Because for each transaction we do we lose some X minus Y amount of currency. So if we just do multiple transactions, so if we have something like X to Z to Y, right, you would lose some amount in each step. So this is always better. Okay, so we should only make one direct transaction. So essentially, all the money from one bank should transfer to the bank you're trying to maximize the balance in. So this is the first observation. Second observation is, suppose we have some, say, B amount of currency, right, in the bank. So first transaction makes it B minus X, then B minus 2X, B minus 3X, right? Suppose we end up with something like uh, let's say B dash after all the deductions, which is less than X. So at this stage we cannot perform any more transactions from this, because in this case, for example, we had 8 initially, rejected 5 and in 3, and now we cannot do any more transactions because this is less than 3 and we need 5, at least 5 or exactly 5 to perform a transaction. So this is the amount left over. So essentially we can deduct at most, so the number of transactions we can do is at most is A of I by X. Okay, lower bound of fi, right? Because lower bound because we cannot remove the new remainder which is remaining at the end. So this is the maximum transactions we can do of a single bank into y. This gives us the amount of money we are transferring to the maximum bank. Okay. So essentially, for each AI, let's create a new array bi, which is equal to a of I by x into y. This gives us the maximum amount of money we can carry over from some ith bank to another jth bank, right? So basically, if we choose some j bank to be the maximum, for each bi not equal to j, we will carry over bi amount of currency from ith bank to the maximum jth bank. So basically, suppose if we assign the jth bank to be the maximum bank, right? The maximum bank will be located. So answer will be a summation I not equal to j b of I, which is basically the maximum amount of money transfer from the ith bank to jth bank plus the balance at I, balance at j, sorry, balance at j, maximum, the already existing balance at jth bank, because we are not transferring any of them. So this is the maximum amount of balance we can achieve at the jth bank. So our solution is to just first construct B, array B. This is just a simple transformation, so it's just linear time algorithm, and then second we just find maximum balance at J. So if we consider J to be the maximum bank, how much money we can end up with at Jth bank? So it's the formula for this. So we can just do this two steps to actually get the maximum possible balance we can achieve. So if you look at this solution, this one. Yeah. So first I compute the send or the B, which I discussing, that is the maximum amount of money can transfer from one bank to another bank, ith bank to jth bank, and then for each bank, if I consider it to the maximum bank, I calculate the amount as the maximum sum of the amount from the remaining banks and the amount currently present at the side bank. So I take the maximum over all these I banks. Okay, so now for the third problem on C, this is a really nice problem. Basically, what this problem says is we have k strips of length n. Each strip is basically a string of length n, and we can construct a new string, or we can decipher a new string of length n by taking the ith letter of any of the strips, right? So, for example, if we have say A, B, C, B, A here, we take A from the first string. For the second letter, we take A from the second string, and again A from the third string to get the character string A, right? Also, another thing it mentions is informativity of a string, which is basically the minimum positive integer d, such that the entire string S is a repetition of some string of length d. For example, suppose if you have a string of A 4 times, the informativity is 1 because basically in this string we have a string of length 1A repeated 4 times. Similarly here ABCD we have a string of length 4 as a whole. So because there's no repetition, so the informativity of this string ABCD is 4. Similarly, if we have something like inf, here a string of length 3 inf is repeated 3 times. So the informativity is 3. So to find out what is the find out the string from the deciphered steps, just the max minimum informativity. Okay. So if we consider this example ACBD and BDSC, uh, ACBD and BDAC, right? One solution could be to, let's say, take the first A from the first position, then maybe let's take D from the second position, then maybe B from the third position, and then D from the second position. So for this case, the informativity is only 4, because no matter what we do, we cannot find any repetition in the string. All, like if we take AD for example, this cannot be AD. This cannot be the informativity because the second part is PD. There's a mismatch between these two parts. Right? So the informativity here is 4 only. If it was AC, right, then you can take A in third position and C in the fourth position. It is 2 because we have the string ACAC repeating. So it is then 2. Informativity 2. Right. So one way to solve this, suppose you want to check check if sorry check if we can get informativity, let's say just call it info, it's long info of length k, right? So what I mean is, if we can get a string whose informativity is k. Okay, so first thing first, n has to be divisible by k. Okay, this has to be possible, because if it's not divisible, we cannot, because the string is constructed by repeating another string of length k, right? So obviously n has to be a multiple of k. So n is firstly divisible by k, all has to be. Other, the string is of the form t or something like this, just it's each t of being of length k, right? Each t being of length k. Now to solve this subproblem, this is a quite a simple, like a pretty simple solution. Suppose we compute the frequency of each character, or say frequency of I of C, stores the frequency of C at all strings in the ith position, right? So what I mean is, if we had the original example, A, B, C, D, A, B, C, D, what is yes, A, B, C, A, B, A, C, B, D, A, C, B, D, B, D, A, C, right? A, C, B, D, and B, D, C, B, D, and B, D, A, C. For the first position, the frequency array is, for the first factor A, we have one occurrence, and B has one occurrence, right? Again, for CD, C has one occurrence, and D has another occurrence. So you can consider, say that this is the frequency of the column, you could say, like each column separately and calculate the frequency of factors in this column. So the utility of this is, there exists a string T with T of j, the jth factor in T, equal to C only if uh, frequency of j of c is greater than. What this essentially means is we can build a string whose jth position has the character c if the frequency the jth position for character c is greater than 0. So you can see this is essentially pre-computing what characters we can have as a jth position in the deciphered string. Okay. So now suppose in this case, if you complete the entire thing, we have for this position we have B1 and A1, right? Nice. So now that you have completed the frequency array, suppose you want to check if we can end up with a let's say we end up with k equal to size 1, k equal to size 2. Okay. So in that case, our s of 1 has to be equal to s of 3 because we are taking these two and these two is equal, right? So s of 1 equal to s of 3 and s of 2 equal to s of 4. Now what was frequency of 1, right? This was a comma b, right? So a equals 1, b equals 1, and frequency of 4 was uh, d comma c. Sorry, frequency of 3. Sorry, frequency of 3 was b comma a. Now if we take the intersection, right? The intersection of these two is also a comma b. Now suppose we have another uh, a longer string, something like let's say, and that we have a string of length 1 2 3 4 5 6 and frequency of 5, but something like c comma p. So in that case, the intersection would become 1 comma 3 comma 5 become b, because a does not occur in this 5, so the intersection of all these three frequency arrays becomes just array b. So what this essentially means is, if we build uh, if we try to have an informativity of length 2, the characters at position 1 3 and 5 must all be equal. So it must be a character from the intersection of the frequency arrays. In other words, for example, if we consider just 1 and 3 of, then it can be either a or b. If you consider all these 3 1 3 and 5, it has to be b. So the first character is b in the string t which will be repeating is b. Is what this means. Okay. Similarly, for let's say 2 and 4 or 2 4 6, we can find intersection and check if it has an answer. Now the one important thing to note here is that suppose for a simple case we have something like a b c d. Okay, for this frequency say comma c b comma d, if we try to take informativity of length 1 or k equal to 1, then their intersection is null, right? So this means basically since it is null, there cannot be any repeating character between these two positions. So essentially this means that uh, we cannot have an informativity of k equal to 1, right? So the case 2. So if you want to have the informativity of k, just go through each kth position and check if their intersection of the frequency is null, not null. If it is not null, you can just pick any element from the intersection. Okay. So for example, for this case, frequency of 1 comma 3 is AB, and frequency of 2 comma 4 is CD intersection CD, so CD only. So you can have either something like let's say AC. So T can be either AC, or you can take AD as well, or BD. So any possible combination of the of these two, right? So like if you're taking the first factor from this set, second from this set, and so on. Okay. So to summarize in solution, firstly we compute the frequency array. This is just this can be done in n to k. Like we compute. Okay. So this one thing is when we're iterating. So firstly, for each k, we firstly already compute the frequency array, right? The compute frequency array, it takes order of n into k time. Now for each k, check if k is possible. Okay. Now this is going to take order of n time, because we are just going through each kth position and checking if the frequency of the intersection is uh, like not null, like there's something in the intersection. So you can just take any character from the intersection and reconstruct a string t. So the overall list is just n to k, right? So if I just show the solution really quick to make things clearer. Firstly, I go through the string and compute the frequency array. Okay, like I mentioned. Then I try each informativity length. If it's okay, there's one thing I just so there's one thing I did wrong. So for each k I'm doing, right, we check let's call this not k, for each say length x. Okay, for each length x we check if we can have s with info x, right. Now this check itself take order of n time, and I've sorry for disambiguating it, but this k is the number of strips, right? This k is number of strips, and this is the length of the string. X is the length of the substring, or the repeating part. Now this x itself can be from in length 1 to n, right? So it might appear that we have a solution of order of n square, but this is actually not the case, because I'll tell you why. Because even though the actual possible, we can have informativity from 1 to n, and it check text order of n, so it's order of n square, but it is not n, because as I mentioned in the previously, that the length has to be divisible by n, right? It has to be divisor of n. The number of divisors of n is something like so the order is roughly n to the power 1 by 3. There are many proofs for it, but this is roughly the order for the number of divisors in it. Okay. So essentially, if we just consider the x's, which are only divisors of n, we can do it in only order of n by 1 by 3 into n time. and this is sufficiently fast for a solution. So that's why this solution works in time. Okay, because we are quickly eliminate if a value of length is or x is not divisible by n, we are eliminating immediately. That's why it works in time. Okay, so build the frequency area, go through each length of the repeating sequence x, and check if we can have. So here I just check find an intersection of the of all the frequency at the every ith position, and if there is any occurrence of there is some intersection of characters, we just append any character to the string. So you can just print the first for the first length where this check passes, you can just print the string immediately. Now for problem D, yeah, this is a really nice question actually. So it is given that you have a string of matrix of length n of size n by m, it's less 0 or 1. You have to cut the matrix into two parts, right, and up and down, upper and lower, such that if the number of ones in the upper part is a and lower part is b, you have to maximize the value of a into b. So for example, in this case, we are in the first part, we have a 1 2 3 4 5 ones in the upper part, and 1 2 3 4 5 1 2 sorry 6 in the lower part. So the product is 30. Similarly here we had 1 2 3 4 in the upper part and 1 2 3 4 in the lower part. So the summation is 16. Product is 16. Not 16, sorry. 1 2 3 4 5, sorry. 5 and 4, so 20. Now for this question, just a very easy observation is, firstly, our best possible answer is p equal to count of 1, that is the number of ones in the matrix, by 2 into count 1 by 2. Basically, we are evenly distributing the ones between the upper part and lower part to get the maximum possible product. Okay, this is the first observation, and I will also show that you can always construct a matrix like this. So in order to do that, let's take this example 0 1 0. Okay, let's change the color. Yeah. So we start at this. So we're starting the cut here, right? Now, suppose we go down at this position, right? If we go down, what this implies is we are essentially taking this entire first row for the upper part. So our summation increases by 1, right? Now, suppose if we go even further down, we take this entire second row. Okay. So we end up with another 3 here. Suppose we go right here, again right here. If we go down now, again we are taking this third row, but we're taking the third row from the of M, like the, if you consider the number of the columns here, in the third row from column last column 4 to third column. So here it becomes 1. Okay. Suppose we go right here. Again we go down. So we take the 4th column, and from 4th row we end up with this, and let's say we do it like this here. Or let's skip this because this is not optimal, right? So let's do it like this. Yeah, we take the like this, and that way our answer becomes 5. Okay, so 5, and the upper and lower part is 4, so 20. Uh, so what I need to show here is that uh, whenever you make a down move, essentially what happens is you add up all the columns to the left of the current position for the given row, right? So we can have a greedy approach. So if let's say uh, if sum plus, let's say or let's call this s of I of L to N. So what this means is uh, if our current sum plus all the elements in the ith row from L to the last position does not exceed this count 1 by 2 value, which is the half of the number of ones, or take a down move. Okay, this is the optimal solution. There are many ways to prove why this is optimal, but the gist of it is that uh, we have something like this. If I take a better example, it will be easier to show you. Let's take 1 1 1. Let's see, 1 1 1 1 1 1. Okay, this is yeah, this works, I think. So total one count is 1. So you have to convert it to something like 4,5, right? So one part has 5, lower part is 5. Suppose we want upper part to be 5, okay? So when we start our first move, we see that for the first move, our S of 1, I currently at the first position, so 1, N. This entire sum is 3, right? Our current sum is 0. So we can take this first part, entire first row, okay? Now for the second step is we are the second row now, and we have still the first column of 1 to N. This is again 3. Now notice that if we take this the whole thing, we'll end up with a sum of 6. This 6 is 5, right? So we cannot take this sum. So now we ignore this row and move forward. So now our uh, column becomes 2. So now S of 2 of N is 2. Now we can take this because our sum is 3. If we add, we get 5, which is does not exceed the target of 5 itself. So we convert sum to 5 now. Now again, if we consider the next in next row, we have added 2, we cannot add anymore, so we take right again. Again we take right because we can't add anymore, and we end up with this cut. Now the reason why we can always achieve this is, suppose uh, suppose we are at some we have some target uh, x, right, and the sum plus current row is x exceeds x. So what this means is there is some row like this from L to N with a value uh, with a very large value. Okay, sum plus y. Uh, Suppose we need to complete this. Suppose this is greater than uh, x minus sum. Basically, what I'm saying is now if it's greater than x minus sum, we know that our matrix only has 0 and 1. So there must be some index smaller which has exactly x minus sum, right? Meaning if we perform the down operation at a later stage, we can achieve exactly x minus sum and addition and get our target x. So this is why the greedy approach works so well and correctly. So we can just perform down operation and take the whole row whenever possible, and this will give us the great answer. So if you look at the code quickly, yeah. So here what I did was I just computed the prefix sums to quickly calculate the row sums I was showing. Right. You can. This is multiple ways to do it, but you can do it like this as well. So compute prefix sums to get the row sums quickly, and then as you iterate through the row, if the current sum plus the sum from the current row is less than the target sum we're achieving, we add it and perform a D operation. Otherwise, we skip the row. Okay. And at the end of each column, we add an add operation to move to the next column. So this is us the answer. Great. So finally, the last problem for today. So for here, just to get a quick summary of the problem, I'm just going to go through it in detail. So I'm not go through it in detail, but essentially what we have here is we have a matrix of matrix A of size n by n. Each matrix has each cell has value a I comma j. So firstly, we have to find the path from AI from 1 comma 1 to n comma 1, just the largest sum, right? This is what the problem is. Now another opponent can make a move which is flipping the value of a cell, so we can change the value of ai comma j to a minus aij. So to find what is the best possible what is the cell we should invert such that the maximum path sum is minimized. For example, suppose in this case, in this matrix, the initial path was, if we show this quickly, here in general, like without any changes, the best path would be this, right? The sum of 1, 4, 5, 10, 1, 4, 5, 6, 10, 11, right? Suppose we change it, we flip this cell, right? In that case, it becomes 1 minus 6, 1. So now our best part should be, we can do something like this: 1, 4, 1, go here, and go here, and then here. So 1, 4, 5, 0, 2, 3. So here it is 3. This is the minimum possible, like the minimum distance as far as we can minimize the change. So to find out the maximum, the best change we can make so that the maximum path in the matrix is minimized. Okay, so suppose I'll just quickly declare some important things we'll be using. Let's call s of I comma j to be the maximum path from 1 comma 1 to I comma j, right? And d of I comma j, maximum path from I comma j to n comma m. And this is in the original matrix, okay, without any changes. Fine. So I'll declare one more thing. Let's call this path only. Path I comma j. Path I comma j is maximum path distance such that it passes through so what this means is when you find a maximum path such that the path is going through I comma j. So essentially 1 comma 1 to some in some point you will pass through I comma j to I comma j to n comma m. In fact, there is a relation between these three, which is that uh, path of I comma j is equal to s of I comma j. So maximum path from 1 comma 1 to I comma j plus t of I comma j minus the value. So whatever the value was set. So like the original matrix, whatever was. We take this because we are double counting the value of the cell Ij at both these like these two. So I'm just detecting it. Yeah. So this is what the value comes out to be, right? Uh, so this gives us the maximum path from any for any Ij such that the path passes through I comma j. Now suppose in some matrix, if I draw a very large matrix like this, suppose uh, we flip or change this cell, right? So now you have to find the maximum uh, distance in the matrix, maximum path in the matrix after inverting this cell. Okay. So one candidate is the path. Now what happens to the path going through the I comma j itself, right? What happens to it? So it becomes path of I comma j minus 2 into a of ij. Again, this is very simple because since you're just flipping it to negative, so the path value becomes is subtracted 2 times by this cell. So this is one possible path in the new matrix. This is the path to I comma j. Now there are two other possible scenarios. One is when passing the jth column, our path goes to the top of the above this cell. So it can go like from like here or maybe like this, right? So what this means is we are going to ignore this I comma j cell and go from top of it. Right. So this is actually a minimum of of j less than j dash less than j, path of I minus 1, sorry, minimum of sorry, minimum of I dash less than I, right? So any row above the current row and path of I dash comma j plus 1. So what this basically means is it is all the paths which ignore I comma j cell and go from top of it. Okay. And we take j plus 1 because if we had taken j, it is possible that from j it will go to j dash, like if you had taken sorry, if you had taken j plus 1, because if we take j, it is possible we go from this I dash to I directly from by down. So you have to take j plus 1 instead. And this will give us the correct answer, because regardless we have to go to some cell in the next column regardless, right? So this is one possible candidate for the mini axiom path. Another is we can go from below it. So see, so here to here, something like here to here. So this bunch of cells. So if you can go from below it, I dash greater than I, path of uh, I dash and j minus 1. Again we take j minus 1 because if we had taken j, it is possible to go from j to j minus 1 go from go from I dash, from I here to I dash by going down. So we take j minus 1. This ensures that it counts all the cells which ignores I comma j and goes from below it. So these are three possible candidate paths. And basically what we do is we take the maximum from all the, okay, sorry, I made a mistake, should be a maximum, but yeah, should be maximum, right? So we take the maximum from all these three sets and whatever is the answer is. And for these two you can just calculate the prefix for the path matrix we got, a prefix and suffix, to quickly get the maximum like this. So this all of these takes order of 1 10 to compute, right? And we go over each cell, we try painting each cell and check what is the maximum distance after painting this cell or flipping this cell, whatever. So this becomes order of n into m time. Order of 1 to check each cell and order of n into m cells. So I'll not go over the entire implementation. There are many ways to do it, honestly, and I can share my code later if you want to check how you can implement this queries to find the maximum and minimum suffix prefix like I showed. Basically, I build the path array like this, like I discussed: source plus destination minus the current cell. Then I compute the prefix of the cells up, so the rows above and the rows below the suffix. And I have three different cases, considering the I comma j cell with the painted version or the flipped version, considering the paths above it, prefix of I minus 1, and paths below it, suffix of I plus 1. And the maximum over this gives me the maximum path in the flipped version. Okay. So that was all for today. I hope you enjoyed the solutions, my explanations. Please do like and comment on this video if you like my explanations. Also, please make sure to check out Kepler's website for the notes for this video as well as other resources. So that is all for today. Goodbye.